Hi, I'm Zach with HKN, and today we're going to make the final video in our series about Maxwell's equations, and this final equation is called Amperes Law. So this is its differential form. We have the curl of the H field. Okay, so let's actually just note up here, the H field is pretty simply related to the B magnetic field, which is probably what we're more used to dealing with, given this relationship here. Actually, yeah, this is B over this constant mu naught, which is permeability of free space, I believe. But this equation, there's one less constant we have to work with if we do the equation in this form, so we'll do it like that. So, like all the other ones, this is its most explicit form, I guess, but it's a little bit hard to visualize what it's saying. So we integrate. We're going to integrate and get a different form of it. Now I have curl, which is the tendency of our field, our H field, to rotate around a single point in space. So we'll integrate that over a surface, a not necessarily closed shape surface, just a bounded surface, and we'll see what that does. So so when we do that, the curl, the integral of the curl over a bounded surface becomes the line integral around the outside of the, around the line bounding our surface. We'll call that line C of H, dotted with our differential length that we're integrating through. So that is this side of the equation. And then, okay, I guess we should come back here for just a second and explain what these terms are. This J is called current density, and it's the amount of current flowing. So when we integrate over the surface, it's going to be the amount of current flowing through the surface. It would be, this would be equal to the integral over our surface of J dot dA. Plus, we'll also integrate this term over a surface. Now this is, as we can see, is a time derivative of an electric field, and we'll see how that comes into play later in this video as well. This would give us the integral over the surface of, this is a constant, we could have pulled it out in front of the integral, of the time derivative of E integrated, dotted with the differential area. So let's simplify this just a little bit more. So this term actually is going to have to stay pretty much the same. But what is this? This is the amount of current flowing through our surface. So we could really just refer to it as the current enclosed by our by the bound of our surface, right? If we'll draw a picture and see how that works. But we'll call this the I enclosed by our bound, and we'll say plus this constant integral of the time derivative of the electric field. Okay, so let's draw a situation where these things could come into play here. Let's imagine that we have a current carrying wire, and let's imagine that we put, actually, maybe make this a little farther into the board. So we have our wire, and also let's imagine that there's a capacitor in our wire. We'll make the plates round for nice symmetry. And our wire would continue this way. And say we have a current flowing in our wire, I. Now, no actual electrical current flows through this capacitor, but we'll see how that works here. So we know that inside this capacitor, we would have an E field, right? Flowing from the plate with positive charge on it to the plate with negative charge. So we'll mark this plate. Let's see. Plus Q for positive charge. That's a pretty terrible Q. And this plate down here is negative Q. Actually, we'll just keep that in mind. Less jumbled. And let's say that this plate has, let's say this plate has area A. Okay, so now we are going to use Ampere's law to find how the magnetic field behaves in this situation. So one little convention that we use, we can actually prove this convention with something called the Biot-Savart law. We won't get into that. But when we have a current flowing in a wire, we know that it's going to result in a magnetic field from this, but which way is that magnetic field going to be pointing? So we're looking for the current enclosed by a loop, so we can draw our loop wherever we want to. And we want current to be flowing through the surface that's bounded by that loop. So we're going to draw our just imaginary surface. Let's draw it like this, where that circle encloses that wire. And let's just imagine that the wire is also in the center of that circle. And let's imagine that our circle has radius r. So what Ampere's law is saying is that due to this current flowing through this surface here, there's going to be some magnetic field around the edge of this. So this would be our path C in this integral here. So according to our right-hand rule, the direction of the magnetic field is determined by, if we point our thumb in the direction of the current, the fingers of our right hand will curl in the direction that the magnetic field will point. So in this case, our current's flowing down. Our right hand fingers curl that way, so our H field is going to be pointed like that. And it'll be pointed like that. It'll be parallel to the edge of the circle at any point around the circle. Does that make sense? It's really a circular field around this wire like that. So let's try to find what the magnitude of that would be. So I guess we'll start here. So we said we'll use Ampere's law, and we'll actually be able to take a term out of it for this particular point right here. There's no electric field in the air around this wire. There is also no electric field in the wire, right? Because inside of a conductor, there's charges arrange themselves, so there's no electric field. So this second term in Maxwell's equation here is going to be 0 for this case. So we can rewrite Maxwell's equation to be the integral of H dotted with our differential path length is going to equal the current enclosed, right? Yeah, the current enclosed by this path. Now, we set up this problem. This works for any line integral. As long as you pay attention to this dot product, it will work for any path you could draw around this wire, but we set it up so that we have symmetry, and the magnitude of the H field at any point around this path is going to be equal, and we have that the H field at any point along this path is going to be perfectly parallel to the differential length of the path. Does that make sense? So this dot product will just become, this integral of this dot product will become H times L, where L is the total length of our path, is equal to the current enclosed. And what is the length of our path? We have it as a circle with radius r. So this becomes H times 2 pi r, right, is equal to I enclosed, or H is equal to I divided by 2 pi r. So that gives us, regardless along this wire where we put this surface, that'll give us the H field at the outside edge. And what did we say the direction was? So this is a vector, right? So we have to specify what its direction is. We usually do that, I guess, the most convenient way to do that is in cylindrical coordinates. And in cylindrical coordinates, this would be multiplied by the unit vector in the phi direction, because yeah, phi is perpendicular to r. So that will give us our magnetic field anywhere along this wire, but we want to know what would happen if we pulled this surface a little bit farther down and had it sitting in here. What would happen then? Because we know this is a capacitor, correct? And we know that in between the plates of a capacitor there's an insulating material, right? And electric current doesn't actually flow through in between the plates. Charge collects on the plates and can't pass from one to the other. So we'd like to know what happens to our H field here, what it looks like, if there is any even. So we'll extend our, well, we'll redo Ampere's equation, or Ampere's law. But first we have to do a little bit of other work, and it's going to recall our first video. So we're going to try to describe, actually, I never indicated it, but there's an electric field here, right, in between the plates of the capacitor. That's what those vertical arrows are. So we need to know what that is. We know from, okay, so let's just write the Gauss's law that we did, first video we did. We said that a, what was it? Over a closed surface now, a surface enclosing some volume, the electric field, the surface integral of the electric field dotted with our differential area was equal to the Q enclosed by that surface divided by this epsilon not constant. So if you go, you can just see a pretty good explanation for this if you go back to our first video in this series. But we're going to use that to solve for the electric field here. So we said that our, let's see, we said that our capacitor plates are going to be charged, right? They're going to have some electric charge on them. And imagine that we drew our Gaussian surface that needs to be enclosing a charge. Actually, let's just extend these imaginary surfaces. And now we have an enclosed cylinder that's enclosing the top plate of this capacitor, right? So this is the bottom of the cylinder in between the plates and the rest of the surfaces above it. Now, we know the charge that's being enclosed by the surface is Q, right? And we also know that the only place electric field is flowing through this surface is at the bottom. And we know actually this is a uniform electric field, and it's has area A. So actually let's rewrite this equation to say Q. We'll say Q enclosed is equal to, we'll move this constant up, epsilon naught, the integral, okay, so since we know the electric field is only flowing through the bottom, the dot product of E and the area everywhere else is going to be 0, right? There's no electric field flowing through any of this surface up here. So we really only have to worry about integrating over this bottom area. And that gives us And that also is going to be equal to this epsilon naught times E times this area A, right? The only place the electric field is flowing is in this area. So, so that is the charge on this plate of the capacitor. Okay, so what do we want to do next? So we have a definition for current. Current by our definition, we have that I is equal to dq dt. It's the time derivative of the charge through a surface. And that holds for the charge on this plate. The time derivative of the charge on this plate is going to equal the current flowing in this wire. So we can say that if this term is equal to Q, then the current in the wire is equal to the time derivative of this term. And we will get that that is epsilon naught, the integral over this bottom surface here of the time derivative of this term, which is going to be the time derivative of E, correct? The area isn't changing with time, so the only thing actually changing with time is E. It can change with time is E. And that it will be dotted with dA. And now that looks exactly like the second term in Maxwell's equation. So this is something we call a, what is this called? Displacement current. It's not an actual current in terms of charges moving, but it is just as valid of a current in terms of physics. So now let's redo Ampere's law for the surface that's in between these two plates. So we would have that the line integral around this path here of H dotted with our path is equal to, now this time we can set the I enclosed term to 0, correct? Because no current is flowing in between these. We'd have 0 plus a term for our displacement current, epsilon naught. And what did we just say this was equal to? From our reasoning down here, this term is equal to the current flowing in this wire. So we say that, and we have symmetry, so we can say this is H times L is equal to epsilon naught time derivative of our electric field, and that is equal to I, right? So that tells us that if we say H times 2 pi r, where the surface still has radius r, is again equal to I. And so H, yeah. Let's just keep in mind where this H is. It's equal to I. Whoops. So again, we get the same exact thing. And the direction convention is also going to be the same. It's going to be in the unit direction of phi. And that's actually a pretty interesting result. We get that the H field here. So this was our H field from the current, and this is our H field from the displacement current. Let's call it H sub D, just to keep them separate, but they are equal. And that is an interesting thing. Actually, Maxwell was the one who added this second term to this law to account for situations like this. So now we know that if, okay, so actually, let's think about what a capacitor is for just a second. The only time a current is going to be flowing into a capacitor is when it's charging, right? As soon as it's charged up to its capacity, or to the capacity that the voltage allows, it acts like an open circuit, no current flows. So, but anytime the capacitor is charging, or anytime there's an AC current flowing in it, there will be a magnetic field around, even around the edges of the capacitor, due to this term in this equation. So, so yeah, that's it. That's it for this. Thanks.